thank you all for being here and for being ready to be tortured by attending this talk. So in these 25-ish minutes, I want to introduce this family of groups, which is called the family of rearrangement groups of fractals. And I want to spend a few minutes to explain what goes on with the conjugacy problem and how you can tackle that. This is mostly to give you an idea of how the groups work without really delving into the technical details, because it's a fairly short talk. And I instead want to convince you that these groups are nice and that I enjoyed it and I think you should enjoy them too. And that the conjugacy problem is nice in these groups in the sense that you can do computations in these groups in a fairly nice combinatorial way. So first of all, the idea of these groups is all codified by a pair of graphs. So everything starts with something that is called the replacement system. The idea of creating fractals with replacement systems or with graphs that can be expanded and modified and that approximate your fractal is nothing new, really. It's probably decades old, goes back to Thurston, I think. But the nice thing about the latest iteration, I think, that is due by Jim Belk and Forrest in 2019, the one that I'm using here, is that this also really naturally creates these family of groups acting on these fractals. So this is why I'm using this notion to define all of these. A replacement system, then, is simply a pair of finite graphs. The first one is called the base graph, and the second one is called the replacement graph. The second one is equipped with an initial vertex and a terminal vertex. These simply need to be distinct vertices of the graph. So these terms already give you an idea of what you should do with these graphs. And this replacement system defines a rewriting system in the following way. You start from the base graph, you choose an edge that you don't like, and you replace it with the replacement graph. With the replacement graph by attaching the initial vertex of the edge in place of the initial vertex of the replacement graph. And the same happens, of course, for the terminal vertex of the edge. So I'm going to give you an example in 30 seconds. I want to make it clear that the idea here is that you start with the base graph. You can replace edges, as many edges as you want. You can continue replacing, and you get then a sequence of increasingly more complicated graphs. This sequence kind of converges to a topological space. This convergence is not something I'm going to explain fully because the definition itself is not super easy. It's also not difficult, but it requires you to look at it and think about it for a while, which is not something you can do in a talk. So I'm going to go with the definition by pictures instead. I really hope you trust this picture and the idea behind this example, essentially. In this case, the replacement system has two graphs which are the same. So the base graph and the replacement graphs are the same graph. It doesn't need to be like that, but this already tells you that nice examples are, like even simple examples can create some interesting spaces. You start with the base graph, which I've drawn again on bottom, and you choose an edge, right? Let's say the one on the right. So when you replace it with the replacement graph, you are replacing it with a cross of 4 edges, essentially. You can replace a new edge here, like this one, and you get a new smaller, let's say smaller cross, kind of. So if you have this idea in mind that you need to replace everything that you see at each step and take the limit, you probably see that you will get something that looks like a tree. But you should think that whenever you have an edge between two vertices, you are going to replace that edge eventually. And when you replace that edge, there is a new edge, there is a new vertex in the middle. So the object that you obtain, of course, is not a tree, but it's kind of like a tree that is densely populated by vertices. And so this is the shape that you obtain, essentially. Now, this space is a Warshawski dendrite of order 4, whatever that means. We don't really need to know what exactly this space is. It is just a nice example that you can create very easily with these kind of replacement systems. Now, very easily, because I'm hiding a few details again, I'm not really telling you how you obtain the fractal. This is more than just a visual approximation of the fractal. You can actually define these limit spaces of replacement systems as quotients of Cantor space under an equivalence relation. The Cantor space would be made of infinite sequences of edges. So the alphabet is made by the edges of the replacement system, and the equivalence relation is determined entirely by the graphs that you obtain by replacing things. So really, the main takeaway here is that the topology of the space, everything about the space, is entirely codified by the graphs of the replacement system and the graph expansions. So the things that you obtain by expanding edges from the base graph. These spaces are defined. This relation is an equivalence relation and then defines a quotient space under some very mild conditions. And when this stuff is defined, when everything works out well, then the limit space is compact and metrizable. So it is a nice topological space. These are a few other examples that I really enjoy, I really like. These are all Julia sets. For those of you who know, these are fractals coming from complex dynamics, but limit spaces of replacement systems need not be Julia set in general, but it's just a very natural source of examples. The ones on the left, which are the airplane on top and the basilica on the bottom, are going to be examples that will appear very shortly. They are going to be, they're essentially fractals on which rearrangement groups have been studied in the past. So I'm going to tell you something about their groups very briefly. Now, I have not mentioned how you actually construct groups. I have only told you how you can construct the limit spaces, the fractals, on which our group is going to act. So let's say that you have fixed a replacement system. It has got its limit space, you fix that. Then the elements of our group are going to be determined by graph pair diagrams, which are graph isomorphisms between expansions of the base graph. By expansion, I simply mean that you take the base graph and you replace a few edges finally many times. As many times as you want, but finally many times. So if you do this twice, you get two different graphs. In general, you would get two different graph expansions. You find an isomorphism between them, maybe, you fix that. That is a graph pair diagram. And the element that we actually call a rearrangement, represented by a graph pair diagram, is a homeomorphism of the limit space that is induced in a very natural way by this. So this is an example of a graph pair diagram. The graph isomorphism here is represented entirely by the colors. So, for example, the red edge on the left is mapped to the red edge on the right, and so on for every other color. And the way in which I've drawn these graphs should tell you how I obtain the graphs as graph expansions. So, for example, in the graph on the left, I have expanded the edge on the right. And then, again, I have expanded the rightmost edge, right? Now, of course, you can do something more formal with codings and finite words over the alphabet of edges. But for now, I think the picture is clear enough to give you an idea of what these elements are represented by. And the graph isomorphism is really inducing a homeomorphism in a pretty simple way. It's telling you that the left portion of the fractal, let's say the one corresponding to the red edge on the left, is being squeezed and rigidly moved somewhere else, which is to the red edge on the right. So these chunks of fractals are simply being squished or maybe enlarged and then rigidly moved around. So you can think of a rearrangement as a homeomorphism that is defined up to some finite precision. It's like a homeomorphism that an approximation of a homeomorphism with an arbitrary precision, but a finite precision somehow. You're only moving finely many pieces around. And apart from that, you are simply rigidly like squeezing them to the right sides, essentially. Now, in this slide, I want to give you an idea of what has been studied so far about these groups, so at least about the examples that I know that are known. So the one on the left is the basilica rearrangement group. The one in the center is the airplane rearrangement group, and on the right, you have the dendrite rearrangement groups. The last one is actually a countable family of non-isomorphic groups. And this table essentially shows you most of what is known about them. So I'm going to kind of tell you the main points here. That is, for example, in the first row, we know that these are finely generated. This does not mean that rearrangement groups are always finely generated. It is not too hard to build rearrangement groups that are not finely generated. But of course, we mostly care about finely generated groups in geometric group theory. So we often study those that are finely generated, right? And it's not hard to find finely generated rearrangement groups in general. So the Basilica rearrangement group is finally generated, but not finally presented, which is kind of surprising because this is a Thompson-like group. I did not mention this, but these family of groups include the main three of Thompson groups, and these groups kind of behave in a similar manner under many points of view, and yet the Basilica rearrangement group is not finally presented, which is very different from how it goes for most Thompson-like groups. As for the airplane and dendrites, we think that these are F-infinity. The airplane rearrangement group is stated to be F-infinity by Belk and Forrest without any proof. And with Davide Perego, we have an idea of how to prove these, essentially as a corollary of something more general, but this is work in progress, so I cannot really state anything precise here. I cannot make promises, but we should get there soon enough. As for the third, fourth, and fifth row of this table, this is telling you that we know a lot about the commutator subgroups. We know that these are finely generated. They are simple, maybe except for the dendrite over the 3, but let's forget about that. In that case, there is a dynamical argument that doesn't seem to apply. We don't know what happens there, but this is just one group in that infinite family. So in general, it seems that the commutator subgroups of these groups are very often simple. And the linearization has been computed. It is finite for the Basilica, and it is infinite in the other cases. Now, we actually know of very nice finite generating sets for these groups, both for the rearrangement groups and the commutator subgroups. And the simplicity is always welcome, I guess, in infinite groups, especially when you have some finiteness properties. So I think that these are all interesting properties to find about groups. And the last row here is for those of you who care about Thompson groups. So if you don't care about them, switch your brain off for 15 seconds. I promise I'll be back without Thompson groups. This is telling you that the airplane and Basilica groups, the airplane and Basilica rearrangement groups embed in Thompson group T, but not in F. The dendrite rearrangement groups do not instead embed in T, but they embed in V. All of these groups, every rearrangement group in general, will embed in Thompson group V, because these groups are based on some prefix exchange transformation on that Cantor space that I mentioned. All right, so this next slide is going to be filled up slowly, not too slowly, by essentially every result that we know in general about rearrangement groups. So not simply about the examples, but more generally about the family of groups. So for instance, the main thing that I mentioned here is that Belk and Forrest, in their original paper they introduced the family of groups, showed that there is a sufficient condition for these groups to be F-infinity. This condition, unfortunately, doesn't apply, for example, to the dendrite, Basilica, or airplane. So it is nice that we have it, but I think that something better can be done. And with Davide Perego, we will probably have a slightly better condition that applies to the aforementioned groups, at least to the dendrites and airplane. We also proved, now this is a joint work with Davide Perego. We also proved that a rearrangement group is, if it is compact open transitive, then it is not invariably generated. Now, these two things are simple to define. A compact open transitive group is a group that can map a large compact set of the fractal, in this case, inside any small open set. More precisely, a proper compact subset can be mapped inside any open subset. So you can think of these as being able to map large chunks of the fractal inside small chunks of the fractal. If a rearrangement group has this property, then it is not invariably generated. What being invariably generated means is this definition. A group is invariably generated if it has a generating set such that if you modify each of the elements by simple conjugation, so if you conjugate each of the elements, you still end up with a generating set. Now, it may appear that this condition is very strong, but yeah, it is a fairly strong condition, but in truth, many groups have this property. Like finite groups have this property, but they might sound trivial. For less trivial examples, the Houghton groups, the Thompson group F, and the Grigorchev group all have this property. So plenty of interesting groups actually have this property. And in our case here, we proved that most rearrangement groups, like all of the aforementioned rearrangement groups, are not variably generated because they are very transitive. They can move large chunks inside small chunks. Now, as promised, I am going to tell you something about the conjugacy problem, and I'm going to spend a few more words in 2 minutes. So the conjugacy problem, in essence, is solvable whenever you have some algorithmic condition that is not too hard to check in this case, but I'm going to explain this a little better in a second, in a few minutes. I think this third point kind of tells a nice story when you pair it with the fourth point here. So in 2023, Urina noted that the basilica rearrangement group is dense in, let's say, a sort of an orientation-preserving group of homeomorphisms of the fractal. This group is like this orientation-preserving group is uncountable. It is a Polish group, so it's a huge group. It is not the kind of finely generated group that you study in geometric group theory usually. And still, he noted that the basilica rearrangement group can essentially approximate every homeomorphism up to any finite precision. I then proved that the same holds for the dendrite rearrangement groups. So the dendrite rearrangement groups are dense in the group of all homeomorphisms in the case of dendrites. And again, I think this paints a nice picture because you have these countable groups that are dense, that can approximate any homomorphism, and yet these groups are still manageable computationally because you can, for example, often solve the conjugacy problem in them. You can study dynamics in them. For example, in the second point here about invariable generation, we use dynamics to prove that. So these groups are, I think, really large and yet manageable under a combinatorial and computational point of view. And the last point here, which is still last but not least, it's very interesting in my opinion, is the fact that the equivalence relation that I defined earlier, like not really defined, but I hinted at earlier, the one that defines the limit space as a quotient of the Cantor space of sequences of edges. This equivalence relation is rational. So it is defined, it is recognized by an automaton. So together with W. Perigon, we actually proved that there is an algorithm essentially that builds the automaton based on the replacement system. And it's a fairly intuitive way in which it builds the automaton. The automaton actually keeps tracks of the edge adjacency in the graphs. So I think this is a pretty neat construction. Now, as promised, I am going to spend a few words on the conjugacy problem. What I want to do, without delving too much into the details, is to tell you how you can do these kind of computations, and mostly pictorially. Like there are diagrams that represent what you want to study in these groups, which I think is one of the nicest things about them. So why am I presenting you with this picture? When you want to solve the conjugacy problem, you often want to find some cyclic thing that represents a conjugacy class. So if you think about the free group, if you want to find the conjugacy class of something of a word, of course, in the free group, you kind of close your word. You think of it as a cyclic word that doesn't have a beginning and an end. So you can think of it as if you have your word written out from left to right, you glue the leftmost part with the rightmost part, and you have like a circular word. And then you can do new reductions that will lead you to a unique cyclically reduced word. We want to do essentially the same thing here. So we need some diagram that has a beginning and an end so that we can glue the top and the bottom, essentially. And this is what I'm going to explain. So the details here are not too hard, but you need to get used to these kind of diagrams. So I don't expect this to be super clear just in a few minutes, but this is really not too hard to grasp with a few examples. So the one on the right here is a graph pair diagram. It's simply an isomorphism of graph, again, as we used before. The one on the left is a Forrest pair diagram for the same element. In this case, you have a top Forrest and a bottom Forrest. The top Forrest represents the domain graph, and the bottom Forrest represents the range graph, the one on the right, for instance. So you can see that there are labels in these forests, and the labels represent the edges. They are ordered per vertices. So for example, the label CT, the first one in blue, represents the blue edge, which is like an edge that goes from a vertex C to a vertex T. So if you actually write down these labels and then you write down what the bottom labels of the top forest represent, it's going to turn out to be exactly the domain graph. This does take a while to get used to, but you can essentially represent the graph pair diagrams with these kind of diagrams, and you can represent the graph isomorphism by gluing the top and bottom forests essentially in a way such that it represents the permutation of edges. So if you believe me on this, like if you believe me when I tell you that a graph pair diagram can be represented by such a strand diagram that represents how you expand the graph, you permute the edges, and on the bottom it represents how you have expanded the range graph. Now we have a diagram that can be cyclically studied. Essentially, it can be closed, and then you get a cyclic diagram. So such diagrams really represent the conjugacy classes in the sense that you can define some transformations on these diagrams that give you a reduced diagram that is in bijection with the conjugacy classes, essentially. So this suggests the following kind of algorithm. If you have two rearrangements, you compute their strand diagrams, which is very easy to do given the graph pair diagram or even given awarding the generators in general. You close the diagrams as I showed you earlier, so the top and the bottom are glued. And then you apply these transformations, these reductions to the strand diagrams. Now, these reductions are not too hard to show, but they're kind of delicate. And they are mostly involved with the replacement system, the way in which you expand graphs. In this case, though, these are reductions. So you need to look at how you can do the opposite, which is how to reduce graphs. If you know about decision problems, you may know that something could be off here, because what I'm saying then is that two elements are conjugate when the reduced strand diagrams are the same. But there might be an issue. You need to have unique reduced diagrams. So if you start from your element, you need your algorithm to conclude with the same reduced diagram. So this is why we need that additional property of the replacement system being reduction confluent. So you need the fact that whenever you reduce graphs, the opposite of expanding, you will reach the same graph, however you take your reductions. This is not super easy to visualize, but it's also fairly nice and easy thing to check once you are given a replacement system. It is not easy to check in the more general context of graph rewriting systems, but we are not in a general context. So in this case, it is not hard to check. It is so easy to check in the examples, though, that we actually have a solution to the conjugacy problem in many groups with these techniques. So first of all, this was only inspired by techniques on Thompson groups FTMV that didn't have any of these issues with the graphs because they essentially didn't have those labels in the diagrams. And it provides a solution to the dendrite, airplane, and basilica rearrangement groups, the ones that I mentioned. Also provides a new solution to the conjugacy problem in the Houghton groups, which was already solved in 2015, but this is a new solution, so I think it's neat. And we also have a solution to the Thompson, to the conjugacy problem in Thompson-like groups, QF, QT, and QV. So you actually hit some groups that do not necessarily act on fractals themselves, but these techniques also apply to them. So to conclude, there are many questions that you could ask about these groups, right? Because these are fairly recent. You could try to understand more about for example, the reduction confluence in the replacement systems, but I think that that is easy enough to check in the examples that it's probably good enough as it is. Questions that instead I think are really interesting are simplicity, because as you've seen, many commutator subgroups seem to be simple, but there is no clear condition under which that happens, at least not until now. So I think this would be interesting to understand. And I think it would also be great if we had some procedure algorithm to list the generators or relations of a rearrangement group, though this might be a little too ambitious. And of course, I really hope that any of you find this group interesting enough to try to have a look at them, study them, and then you can probably study whatever you want about them. And I hope you get to enjoy them as much as I did in the last few years. So thank you. That was everything I wanted to tell you. Thank you.
Okay, let's thank Matteo for his talk. Are there any questions for Matteo?
Yeah, I wanted to ask something. So, could you tell more about these reductions? Like, what should I think them of?
Sorry, about what? The actions?
No, the reductions. Like you have these trend diagrams and you want to reduce them. Like, should I think them of like actual cyclic permutations or something like similar? Or
right, the reductions are. Let me see if I can draw something that would be the best way to go. So you can see what I'm drawing, right?
Yeah, I can. Yes. Yeah.
Right. It's the least I think way to present, but you might have. So there are three types of reductions. The first one are very simple, and these are mostly just because you can represent elements in different ways, and these are not really about conjugacy itself, but they may happen. So this thing, if you see something like this in your diagram, you can reduce it. So it's supposed to be an equivalent symbol, very badly drawn. And these three things, the converge and then diverge, are the same as three separate things. You have a similar reduction when you have like what I call an onion, like trivial onion, which is something that looks like this. It looks more like an onion if you draw it like circularly shaped. And yes, in this case, it's single line. It's like opening a diagram and then closing it without doing anything else. It's the same as not opening. This is really a Thompson-like kind of behavior. The additional one is that when you have loops without any splitting, without any shape like the one that I showed you earlier. And you need to check the labels. So you're going to have some labels here. Oops, the last one is terrible. And the labels here may represent a graph that can be reduced. For example, can represent this graph. Because each of these loops represents an edge in some graph. Of course, I need four loops to represent a subgraph with 4 edges. But in this case, if you see something like this, you can reduce these loops to a single loop, which is the same as saying that when you have the subgraph that is isomorphic to your replacement graph, you can reduce it to a single edge, which is the opposite of an expansion. So this is the link between reductions in closed diagrams, when you have these concentric loops, and reductions in your replacement system. This is not super easy to explain, but I hope that I give you an idea.
Okay. Yeah. Okay. Thank you.
Thank you. Thanks.
Are there any more questions?
Yeah, I have a question. Hi, Matteo. Yeah,
Hi.
thank you for the nice talk. So I was wondering, what can you say about which rearrangement system might create a circularly orderable rearrangement? What can you say about the circular order?
Circularly orderable.
Yeah.
I'm not sure. Yeah, that is an interesting question. I don't think it has been properly tackled. But for instance, for the Basilican airplane, those embed in function group T. So I guess those should work. So for the
I was
dendrites,
wondering
the
that.
issue is that,
Yeah. Sorry.
of course, for the dendrites, I think that the issue is that whenever you have something that looks like these 4 edges attached to a vertex, in theory, there is nothing telling you that you cannot permute them in any way that you want. That is probably going to ruin whatever you like circular kind of embedding that you want to find. And in this case, you can build some replacement systems that do not satisfy the nice condition that defines the limit spaces. And you can kind of force your group to act in a certain way around those points. And so you can probably find the arrangement group for dendrites that embeds into the essentially the group of automorphisms of the lamination of dendrite Julia sets. But that, in my opinion, is not obvious. It is not trivial in any way. In my paper about dendrite rearrangement groups, I have a chapter on things that I wish I could do, but I didn't because the paper was very, very long, and it includes this thing. So there is a construction there that will give you a replacement system that I think acts on the circle nicely and probably embeds in T, that essentially preserves this circular order around the branch points, the vertices of the graphs, essentially the branch points of the dendrite. I'm not sure if this is what you asked me. So is this this answer?
Yeah, that answer is perfect.
Thank you. Okay, so
great.
for dendrites, I think you can check the paper. One of the last chapters should have something about it. It's not too in depth because it was already very long. I think something can be done.
Thank you. That was nice talk. Thank you.